So good afternoon, Professor Wilczek.
Hello.
So I just wanted to talk a little bit about what life as a theoretical physicist is really like. You know, is it all scribbling equations on the blackboard frantically, or is it, is it something somewhat more down to earth?
Well, I'm not sure down to earth would be the right description, but it's uh, it's a process of thinking a lot, all
Yeah,
the time, and in spare moments. Sometimes even when you're not uh, consciously aware of what you're doing, or think you're doing something else. And in my case, often I'm startled by realizing that a problem I was thinking about. Suddenly, I realize that I know how to address it.
yeah,
Sometimes I'm wrong, but I think that I've made progress, even though I was overtly just taking a walk or taking a shower
yeah.
or something else. Or I like to solve puzzles, so I do a lot of puzzle solving. Then in the middle of a puzzle, I've realized that I've solved a problem of physics, or at
Yeah.
least made progress on. But it's the background of all this is a lot of reading,
Yeah,
uh,
yeah,
books and papers of colleagues, going to seminars, talking to people. It's all those activities, and then going off by oneself. I do a lot of work in the bathtub, actually. I
Okay.
like either with or without water.
Yeah.
Uh,
It's a place for.
what usually in my office, I'm talking to people, but not always. Sometimes I shut the door and work there. But,
Yeah.
and I try to take some kind of work with me to sleep at night, so I'm churning away and as I sleep on something. And sometimes I have some concrete problem that I'm struggling with. Other times I'm just thinking about what to do next.
Yeah, being,
Other
just being
time,
creative.
yeah.
Yeah. So it's not entirely isolated work then. So
Oh, not at
there
all.
is a lot of people interaction. You're going to conferences.
Conferences a little bit, used to be more,
Yeah.
but at MIT where I usually am, where people come through all the time, and I
Yeah.
talk to them. I talk to people on Skype, and used to be telephone.
Yeah. Yeah.
uh, yeah, so it's alternating between social activity and isolated
Okay.
thinking, and of course, a lot of the social activity is also with people who aren't present or may even be dead, reading their books and
Yeah.
works and papers.
Very interesting. So you've been very successful. You won the
Uh,
2004 Nobel Prize
yes.
in physics. Can you tell us a little bit about a little bit of a story about that? So I believe you did the work while you were in grad school. So while you were
I
doing.
did the work. The primary breakthrough, I was 21 years old
Yeah.
and a
Fascinating.
graduate student when I did that. Of course, well, actually, most of the central insight that broke through this problem of what the equations for the strong interaction are uh, was was accomplished in a period of just a few months.
Yeah.
Uh, it took several years to work out, and in fact, we're still working out the consequences. But the specific consequences for unification of all the forces of nature
Yes.
and for application to the early universe,
Yes.
uh, those those occupied the next few years.
Okay. So they
And
weren't immediately apparent, but fairly soon after you got the equations down, it was clear
well, the
that
first issue was
they
whether
meant.
they actually described the world.
Yeah.
Uh, that became very plausible in a few years as the experiments the relevant experiments kind of came in.
Yes. Yes.
Really wasn't definitively established, I would say, until the early 90s, since the theory made very precise predictions for certain kinds of high energy experiments.
So these are
Those had to be
experiments at particle accelerators.
at particle accelerators,
Yeah.
right. So you
Yeah.
can get lots of suggestive evidence for the theory and these particular equations based on other experiments, but the really decisive experiments that were absolutely precisely predicted and so forth really was in the early 90s. That's, I think, why the Nobel Prize took so long.
Yeah. Yeah.
Then, since then I've gone on to do a lot of very different things and focused some of these applications to the early universe, to unification, but also things that have nothing to do with the early breakthroughs, having to do with sort of exotic electronics and application of ideas from originally from high energy physics and kind of abstract mathematical physics to trying to describe real materials, and not only describe but actually design new kinds of materials that really exploit the possibilities of quantum mechanics.
Yeah. So using abstract, very technical mathematics to maybe create new materials with interesting properties,
yes.
Useful properties.
Yes.
Yeah.
Right.
Brilliant.
Really bring quantum mechanics to its potential.
Yeah, yeah, that's important. So just on the note of the Nobel Prize, so how did it actually happen? Did you get a phone call one day saying?
I got a phone call. Yeah. Well, of course, one gets a phone call.
Yeah.
But my phone call, the circumstances are, I think, pretty unusual.
Okay.
Because I had thought for several years that it was coming, and so each year I knew when the announcement was going to be, that day,
yeah,
and the hour, in fact.
Okay.
So the night before, I would always find it very difficult to sleep. And 2004 was like that too. I wasn't sleeping, and every once in a while I'd look up at our digital clock that has red letters and see or numbers and see what the time was.
Yeah, and this was something you'd done a few years.
Yeah,
on the trot.
Yeah, at least I'd say for 5 years before that, I was really thought it was going to happen any time now, because the people whose work ours built on and relied had got the Nobel Prize a few years before, and so it seemed very clear that this was the next step. And I know people had nominated us for many years before that, which was maybe premature, but they anyway, so I wasn't able to sleep, and I knew that the announcement was going to come at 12 o'clock Stockholm time, which is 6 o'clock in the morning Cambridge or Boston time, the real Cambridge.
Boston the real Cambridge, yes, yeah.
So I thought if there was going to be a phone call, it would come after the announcement. So when 5 o'clock rolled around, I said, okay, you're not sleeping anyway. You may as well take a shower just in case you'll be ready. So you can be dressed and clean when the reporters come or whatever. But then I was in the shower. It was roughly about 10 after 5. And when my wife came in, with our mobile phone in her hand, and said, there's a lady calling who has a beautiful Swedish accent.
Yeah.
She wants to talk to you. And that was it. But I got out of the shower to take this call. I didn't think I should refuse to take the call. So I took the call despite the ungodly hour.
Yeah.
And so, and I was absolutely, stark naked and dripping wet. And I took the phone call, and that's it. That was it. That was the. She said, "Yes, you won the Nobel Prize." Describe the citation, and so. And the other thing I didn't realize, though, was that besides the phone call coming earlier than the announcement, is that I thought it would be a simple matter of them saying, "Congratulations, you've won the Nobel Prize. Goodbye." But it's not that at all. They wanted to talk about the practical arrangements, how to deal with the press, what you should and shouldn't say, and then many people wanted to congratulate the president of the Academy, the president of the Physics Committee, friends, and so forth. So there are probably a dozen people, each of which wanted to talk to me, and there I was,
still
holding
butt
on to this little phone, and that was it.
Brilliant. Well, I think it's quite apt, given that you do most of your, a lot of your work in the bathtub.
Right,
to,
I do
to
a
win the
lot.
Nobel Prize in the bathtub. Yeah.
Right.
Yeah. Brilliant. All right. So, well, congratulations for that. That's
Yes.
well, it's the biggest achievement one could say. So, moving on to today's lecture, you're going to give for the Darwin Lecture series, Quantum Beauty. Could you tell us a little bit about what you intend to talk about?
Well, the thing I'm trying to address in this small way, and is a kind of cultural divide between science and the general culture in our society.
Yes.
I think it's a tremendous shame and missed opportunity that science, and specifically quantum theory, provides extremely surprising, extremely powerful, and also extremely beautiful insights into the world that people would find their lives enriched if they knew about them.
Yeah.
So I'm trying to convey that in a user-friendly way with pictures and images and historical connections.
Yeah.
Because a lot of what we do, especially now in advanced theoretical physics, is not so practical. Some of it is, but a lot of it isn't. And so our product is really cultural, and I think it's very important. And it's a great product, but it's very important that we actually make it into part of the culture.
Yeah. So in what way is it cultural? Sorry. So what you're doing in theoretical physics, you're not just now advancing
not
the
something-
maths and
it's
the
not
mathematical machinery.
Well,
what's
I mean
what's
cultural in a broad sense. I mean, but I guess I mean by cultural, I mean it's not economic. It's not something that puts bread on the table,
No.
puts people to work, and except maybe in the very long run.
Yes.
So it's something that its real value is to increase our appreciation of the world,
Yeah.
and potentially to enrich life.
Yeah.
But of course, it only enriches life if you know about it and give it a chance. So,
so the barrier to the general public understanding this beauty and being able
Right.
to know about this beauty is the mathematical machinery. However,
Yes.
I know of Garrett Leasey, the surfing physicist who it was pictures. It was a diagram
Yes.
that really encompassed his whole idea was based upon this circle.
So it's
So perhaps there, not only are pictures and and nice images a good way to to get this across to a general audience. Perhaps it also could reveal new insights, and not to patronize it. But
right. Well, right. Absolutely. I mean, and I think a great example actually is Michael Faraday, who was perhaps the greatest experimental physicist of the 19th century, maybe of all time, but he was not mathematically trained at all, and he thought very much in in images and visual images, and it's because of the way he thought in visual images as opposed to equations that he was able to think very differently about the nature of the physical world than the leading theoretical physicists of that time, and introduced a very different point of view, which has turned out to be very powerful as a basis of mathematical physics.
Yeah. Yeah.
The whole notion that space is full of structure, the so-called field theory, was something that Faraday used to visualize his experiments, but it's turned out to be the most fruitful way also to make equations.
Yeah. So we need a few people who are thinking in different ways, not just in terms of formulaic maths. Perhaps some people who are thinking in more abstract concepts.
It's important to step away and just think about how things might be different, how things might be more beautiful. I'm going to actually emphasize that in the last part of my lecture when I talk about sort of the frontiers of beauty in physics. That part of the value of looking for beauty is that you can think of ways of making things better.
Yeah.
They're not beautiful as enough, right? If
You can make them,
you could think
yeah.
of ways that maybe they could be more beautiful, more pretty,
Yeah.
and that's been a guide to how nature actually works.
Or this is yeah. This seems to always be an underlying theme. Is the more elegant a theory, the simpler, not necessarily simpler, but the simpler the ideas, the more elegant the ideas, the more likely it is to be correct. There seems to be a sort of theme, something
Yeah,
that
well,
drives physics.
there are lots of elegant ideas that don't apply to the world, but some of the ideas that you abstract from studying the world do, it turns out, have extraordinary conceptual coherence and beauty and surprise value that might not have been anticipated.
But do you have any philosophical insights as to why, just because something's more elegant, it's more likely to be, or why even the more elegant theories do seem to be the ones that are more correct? Just because something's simpler.
Well, I think it's more the other way around. And nature works that way because it's kind of a back and forth ascending helix of understanding, but we found, in fact, that nature does obey very simple, well, not simple, but very uniform and elegant conceptual equations. And then if you ask why, well, you could say because nature is very symmetrical, very uniform, and also very economical in the kinds of phenomena that she uses to build up the world.
Yeah.
So it didn't have to be that way, right? If we were describing the world of a computer game, say, which is a world, things happen and there are rules and so forth, but the rules would be very, very complicated.
Yeah. And
it could have been that the actual world worked that way. I think that's probably what Aristotle thought, right? You would have rules here and there, and you'd find a lot of things you could put together, and you would understand it. But you shouldn't think that you could boil it down to a very few rules that were very precise and abstract. And it didn't have to be that way, but it does turn out to be that way.
Turns out the simpler, the better, but not just
so
because
far,
it's
so
easier
far
to
at
understand.
least.
So far, okay. Yeah.
And it doesn't always work either, because, for instance, famously, Kepler thought that the orbits of the planets fit into a system of inscribed and circumscribed regular solids, which would have been very beautiful and explain why there were 5 planets if they were thought to be 5 planets at that time. But in fact, there aren't 5 planets, and they don't fit that scheme.
Yeah.
So it's not always your prior idea about what's elegant, what's pretty, what should be, that wins out. But so far, nature hasn't been disappointing in the sense when you find out how she actually works. It's something
Keeps getting
extraordinarily beautiful.
Okay.
Yeah.
Good. Well, there's a history throughout physics of thinking we're pretty much there now.
Yes.
And then there are 5 planets and this theory works, but of course then it gets broken again and again and again.
Yes.
What would you say? We've got the standard model at the moment of particle
Yes.
physics. What would you say the next step is?
Well,
do you believe the standard model is correct, or do you?
Oh, I think there's overwhelming evidence for the standard model having a very, very large range of applications.
Yeah.
And it would be hard to overstate how precise and well-tested it is and how wide-ranging. So it's tremendously powerful, no question. And people have been very busy trying to find exceptions or defects in it, but for decades now. But so far it's held up better, it's only looked better and better.
Yeah.
On the other hand, when we study it as with a critical eye, an aesthetic eye, it's not as beautiful as it should be. It's not. It has different, has several moving pieces, and one can conceive. In fact, I have conceived of ways of improving it that would take our understanding of nature to another level and make things look more beautiful, more unified.
Yeah.
And I think that's going to happen. And I think the ideas have been kicking around now for almost 30 years. And I think they've only looked better and better, these ideas about unification. But the decisive experiments, I think, will come very soon now. at the LHC,
The Large Hadron Collider.
for these ideas. So it's an exciting time.
Yeah,
right.
Brilliant. So, well, thanks very much for talking to us,
Okay.
Professor Wilczek.
Thank you.